Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue to learn about pre-processing in Scikit-learn and look at power transform implementation in Jupyter Notebook. In previous video, we looked at the intuition. Here we will do the actual coding. And just to remind, this is the formula we'll use for the Yeo-Johnson transformation, here circled in orange. And for the Box-Cox transformation, we'll use this particular formula. So let's get into Jupyter Notebook and start coding. Here I've imported three libraries: NumPy, Matplotlib, and preprocessing from Scikit-learn. And these are the versions for the Python that I've installed: 3.8, and Scikit-learn is 0.23. So the very first transformation that we'll do is on the Lognormal dataset. So let's see how that would work. Lognormal, and for this we'll go ahead and create the Lognormal dataset by using the NumPy function. So we'll set the random seed to 0 so that everybody has the same type of plot and dataset. So for original, this is the original dataset that we'll start with. We'll set the mu, that is mean, and sigma, that is standard deviation, to 4 and let's say 1. And then we'll save the data in a variable called log n, so log normal, np.random.log normal. And here we'll specify mu, we'll specify sigma, and we'll specify the size. So these are going to be 1,000 data points. And if we try to plot this, if we plot log n, then this is the data that we are going to start with, and we'll convert this and transform it into a data set that is close to a normal distribution. So the transform for the transform data set, we'll save those values in the variables t1 and t2. So t1 is for the Yeo-Johnson and the t2 is for the Box-Cox transformation. And for each of those, we need a value of lambda. And so we'll initialize those, we'll use the values of lambda as say minus 0.9. And the reason why I'm using these values is because I've already tried a couple of values, and these were the values that seem to work well. And now for creating the transformation loop, we have to iterate through each of these 1,000 values. So we'll use a for loop for xi that is each value in the original data set, which is log n in this case. We are going to use this formula. So the first formula is xi plus 1 raised to power lambda minus 1 and then divided by lambda. So we'll append that to the t1, which is the empty list that we have created above. So here we have xi plus 1, xi plus 1 raised to power lambda. So this raised to power L1, and then minus 1. So I'm gonna put that in parentheses and then minus 1, and then all of this is divided by lambda L1, and this again goes into parentheses. So that's the formula for transforming the first type of transform. Therefore, second type of transform, again we'll use the second formula from the second slide, which was this one. So we have xi raised to power lambda minus 1. So xi raised to power lambda. So here we have L2, and this minus 1, and then divided by lambda. So we are going to divide this by lambda 2, and then we put that in parentheses there. So once this loop runs, we'll have a transformed data set created and saved in the variables t1 and t2. So when we run this, now we should have those data in there, we can go ahead and plot those. So plt.hist, when we plot t1, we see that it's close to normal distribution. If we plot t2, we again have the data set close to a normal distribution. So that's great. What we'll do now is we'll plot 3 of those side by side. So for that, let's go ahead and create a function that can do that. And so we'll use this function repeatedly for all other distributions as well. So we'll name this as plot this, and here this takes in the value of a, and then we'll use the a title, so the title of the plot, and b would be the Yeo-Johnson transformation, c would be the Box-Cox transformation, and we'll do the subplots. So if you remember from the beginner series, to create subplots, this is one way to do it. plt.figure fig size, and here we'll specify the size of figure, so 15 and then 4, and then plt.subplot. We have 3 columns, so row 1, 3 columns, and the first plot, and then we have plt.hist, so a plt.hist, and this is where we use the title for the first plot as the, because the original data set is going to change. And then for the second plot, we have row 1, column number, we have total 3 columns, and the second plot plt.hist, and this is going to be b, and plt.title, sorry, this should be title, plt.title, and this is going to be the Yeo-Johnson Johnson plot, and then plt.subplot, and for this one we have 1, 3, 3, and plt.hist, this is going to be for the variable c, and again plt.title, this is going to be the Box-Cox transformation, and we'll use plt.height_layout so that the plots are spaced evenly, and then plt.show. So this is the function that we'll continue to use in the following rest of this video. So if you want to go ahead and plot this, so let's see, plot this, and we'll specify log n because that's our original data, and the name for that is, it's a Lognormal data set, and then we have t1 and t2, which is the values that are there. And so when we go ahead and plot this, here we can see that this was the original data set that we have now successfully transformed into these 2 plots that are on the right hand side. Now Scikit-learn has inbuilt library that we can use, and we'll compare those results with this. So for the power transform, we again use the preprocessing library and power transformer. So let's see how we can do that. We'll create another variable trans_yj, then we specify preprocessing.PowerTransformer, and within this we specify the method is equal to Yeo-Johnson, and then we specify standardize. So previously we did not do any standardization, but we'll see how we can do that as well. So I'm going to go ahead and copy this, paste it here, and the second one would be BC, so that's for the Box-Cox transformation, so BOX, COX, and so once we have these, we can go ahead and use those for performing the transformation. But before that, we need to reshape the original data set, so we'll do that here, log n.reshape, and this would be 1000 rows by 1 column. So once that is done, we can now go ahead and create the variables to save the transformed data set using the Scikit-learn's power transformer. So we have sk log yj is equal to trans_yj dot fit transform fit_transform, and here we specify log n, And then the same thing for the second one, instead we specify BC instead of the YJ. So these are the two transformations already done. We can try to plot them. So plt.hist sk underscore log underscore yj, and as you can see, it's closer to normal distribution. We can also go ahead and plot the second one, and we see that it's closer to what we had before. Now let's go ahead and create some helper functions that can do the above calculations, so we do not have to repeatedly type the same code. The first one that we'll write is getvals. So getvals, def getvals, and this will take in the raw data set and the values for lambda 1 and lambda 2, and then compute the transform data set that similar to what we had above. So why don't we go ahead and copy this part. So copy this and we'll paste that here. And in this, we'll also add a feature of normalizing the data set. So let's first go ahead and change this to X because that's going to be coming in from here. And then for the normalized data set, normalize, we can change the value of T1 is equal to T1 minus mean of T1 and T1, and then we have divided by standard deviation. So np dot standard deviation of T1. So mean, subtract the mean and then divide by standard deviation. Similarly, we apply the same normalization step for the second transform dataset T2, and that's what we get here. And finally, we'll return the values of T1 and T2 in this tuple. So that's our first function. And then for the second function, so def transform this. Here we'll take an input value of x and the title for x, because we'll add that title to the plot, and we'll use the values that are specified above here. So it's the same code that we'll use. So that's for trans yj, and then transformation for bc. And then we also have this reshaping of the log n. Here we'll have to change it to x because that's the input value coming into that function. And finally we have this transformed value, and what we can do again here is plot this right in the function itself. So if we say plot this, we can specify x, and then we can specify the name of the plot, so x title, and here we have sk underscore log yj, or to be more specific, we'll remove the log from that because it's no longer attached to that particular log. This would be sk underscore yj, and then sk underscore bc. Those are the two helper functions that we created. I just want to make one change here, so we need to remove that. And now we can go ahead and test these two helper functions on the data that we transformed earlier for Lognormal. So we'll set the random seed of 0, and then set the values for mu and sigma is equal to 4 point and then 1 point. And then we have the Lognormal dataset created by using np.random.lognormal normal, and we specify the value of mu, specify the value for sigma, and we have 1000 data points. So we can create T1, T2 is equal to getvals, and we have Lognormal. And again, for values of lambda 1, we can specify 0.09, and for the value of L2, we can specify 0.04. We can go ahead and plot this. So we have Lognormal, and we specify value for T1, specify the value for T2, and that's similar looking plots that we have earlier. And then we can use transform this function to use the power transformer functions from Scikit-learn to see to perform the transformation. And here, as you can see, both the transformation functions seem to be working correctly. So we can now move on to look at another distribution, which is chi-square distribution, and see how we can transform that. So we have chi-square distribution, and in this distribution, we again can start with creating a random dot seed of 0, and then we can create chi distribution variable, and then use np dot random dot chi-square to create the data set using degrees of freedom 4, and we have the size is equal to 1000. So you have 1000 data points, and so we can go ahead and create t1 and t2 is equal to getvals, and we have chi distribution, and now we specify the value for lambda 1 and lambda 2. So let's try 0.005 and 0.02, and then we can go ahead and plot this. Again, we specify chi distribution and chi squared, that's the title for the plot, and then we input the two values for t1 and t2. So as you can see, we were able to change the distribution. It's now closer to normal distribution. For the second plot, we could go ahead and change this to see if it makes any difference. Could make it negative 0.01, and it didn't change much. So let's try if we put a value of 0.3, and that didn't work. So yep, it's this looks pretty much pretty good. We can go ahead and change this, play with the numbers of lambda to get it more closer to normal distribution. Now we can use the transform this function that we created earlier to see how the power transformer from Scikit-learn converts this data set to a normal. So as you can see, this is much closer to a normal distribution. And here we could go ahead and try using negative 0.1 maybe, and we remove the negative sign. Yeah, so it's not, I'm trying to move it towards the left, but maybe different values of lambda would do that. uh, uh, that could be tried there. Next, let's look at another transformation for Weibull. So Weibull distribution, Weibull. So for this, we'll again go ahead and create create a data set using numpy's random parameter. So random dot seed of 0, way is equal to np dot random dot Weibull, and here we specify value of a is equal to 10, size is equal to 1000, and again we calculate the values for t1 and value for t2 using the getvals function that we created above. We input the value of way, and then for lambda 1 and lambda 2 we'll use these values 3 and 2.3, and then we'll go ahead and plot this. So for plotting, again we specify the original data set, and then we specify t1 and t2 after that. Uh, so this extra comma there, when we run this, we can see that the original data set, which is here on the leftmost side, is transformed using power transform into the data set that's on the right hand side, that is closer to a normal distribution. The Weibull also in this plot looks much closer to normal distribution. So the main change, you can see that there is the values are normalized to mean of 0. And this is using the power transformer function from Scikit-learn that has transformed this data set. Moving on, we could also run this transformation on a Gaussian. Well, for Gaussian, we probably don't need to change anything because it's already a normal distribution. But just to show how that would look, we can do the transformation and see what we get as an end result. So we use the value for mu and value for sigma as 10, and then sigma standard deviation is 0.1, mu is the mean, and then we create a variable Gaussian GAU. In that we are going to store np.random.normal, and here we have mu, we have sigma, and then we have the size is equal to 1000 data points. And then we'll go ahead and calculate t1 and t2 using the getvals function, and getvals, and here we specify the original data set and the values for the lambda 1 and lambda 2. Then we'll go ahead and plot this, and for this again we specify the original data set, which is stored in variable GAU, and we also specify the values for t1 and t2. Those are the transformed data set, and as expected they were and still are close to the Gaussian distribution. And we can use the power transformer, so transform this function, and again we use the Gaussian, and we see similar result, where in this case we are started with a Gaussian distribution, so doesn't make much sense to do the transformation, but we see that it does seem to keep it Gaussian. Now the second one, after this we are going to look at uniform distribution. So what happens if we do a power transform on a uniform distribution? And for this again we'll start with the random seed of 0, and then we'll create a variable uni, and then use numpy's np.random.uniform to create the data set. So low is equal to 1, and then high is equal to 10, and we'll have a size of 1000. So we have 1000 data points. Again we go ahead and create t1 and t2 is equal to getvals, and here we specify the values of the original dataset UNI, and then the values for lambda 1 and lambda 2, and then finally we need to plot this, so we use the function we created above and specify the original dataset and its title and the values for t1 and the value for t2. So this is how the transformed dataset looks like when the original dataset is a is a uniform distribution. Transform this, and if we use the power transformer from Scikit-learn, then this is the distribution that we see in the output. So as you can see, it's not closer to normal distribution, but this is just to show that maybe for uniform transform, for transforming a uniform data set, this method of power transform may not be kind of the first choice. In that case, the quantile transform could do a much better job. Other distribution that we can transform, and that is bimodal. And as before, we'll go ahead and create a data set starting with random.seed of 0, and here we also need to specify mu and sigma. So we'll specify the mean as 5, and then sigma standard deviation of 0.1, and we need to create two normal distributions, and we'll merge them together. So np.random.normal, and here we specify mu, we specify sigma, and then size is equal to 500, and then m2 is equal to np.random.normal, and again we specify mu, sigma, and then size of 500, except that here we'll add a value of +1 to the mean, so that the curves are shifted to the right with that extra 1. Now we combine this, so we can go ahead and concatenate these two. Concatenate, and we have m1 and m2, and the axis is going to be 0. Now when we specify these values t1 and t2 to the getvals function, we should be able to get the transform dataset. So BIM, and we'll specify the value for lambda 1 as 0.1 and lambda 2 as 0.5, and we can go ahead and plot this using the Bimodal original dataset. We specify the name Bimodal, and then we specify the values for T1 and values for T2. So concatenate, and that's the that's the transform dataset. And let's go ahead and use the transform this, and again use bimodal. And as you can see, in both these cases, the bimodal distribution stays pretty much as is, as it was before. So using the power transformer to transform either a uniform distribution or a bimodal distribution may not be the best choice. So let's see what a quantile transform can do in this case. So for that, we'll go ahead and initialize the variable qt using preprocessing.Quantile transformer, and here we'll specify that the output distribution needs to be normal. So output distribution is equal to normal, and now when we get the value, so transformed is equal to, we use the qt dot fit underscore transform, and we'll use the bimodal, so BIM. Now we can go ahead and plot this transform data set and see what it looks like. Transform, so the error is, okay, Quantile. Okay, we need to reshape this. I'm going to do that here. BIM dot reshape, and this is 1000 by 1. Now when we run this, so as compared to uh, power transform, we do see that if we use a quantile transformer, we are able to uh, convert that distribution into a distribution that is close to a normal distribution, as we see here. And similar to this, I'm guessing if we try this on a normal distribution, let's see what we get. So for normal distribution, we had created the data set in the variable u and I, and let's see how that works. When we run this, we again see that the quantile transform works really well in cases where the power transform is not able to convert the data set closer to a normal distribution. That was it for this video. I hope you learned in this video how power transform is implemented, and in the previous video the intuition behind power transform, cases where a quantile transfer is more effective in transforming the data set closer to a normal distribution, where the power transform may not be the best choice, such as in case of uniform or bimodal distribution. Please like, share, and subscribe. I hope to see you all in the next video. Thank you.